Hello, and welcome to the SIGGRAPH 2014 course on scattered data interpolation for computer graphics. If any of you were at the skinning course this morning, there was the example-based component of the skinning, so this course is going deeper into the mathematics for that, but scattered interpolation has many, many other applications as well. Just a brief introduction to our presenters. My co-presenter is Dr. Ken Anjo. He is R&D supervisor at OLM Digital in Tokyo. This is the company that does, among other things, the digital effects for all the Pokemon movies. Ken is also co-organizer of the ACM DigiPro conference, which is a SIGGRAPH sibling conference that happened a couple days ago. And as well, he has a long research career. He's published many papers in SIGGRAPH and a number of other venues. One work of his that you may have heard of, at least some of the older people in here, is his tour into the picture in SIGGRAPH 97, which was the first way of sort of inferring depth from still photographs. And my name is John Lewis. I work both at Victoria University in Wellington, New Zealand, and also I'm a programmer at Weta Digital. I've worked in both academics and in the film industry, movie industry, so I have a couple credits, including on Forrest Gump and the Matrix sequels and Avatar. And this lists a couple of publications that are relevant to this course. So our schedule is in 4 parts. So we're going to have a quick survey of applications just to motivate you. That's only going to take 10 minutes. Then we're going to go over scattered interpolation algorithms, and that's going to be sort of a full hour's worth, quite a bit of material to go over there. Then we'll take a break. Then we will go more in depth on some applications of scattered interpolation. Then we'll take another break and come back and talk about some of the deeper theory. So the relationship between radial basis functions and Laplacian stuff, and also relationship, how to motivate all of this through something called RKHS, reproducing kernel Hilbert spaces. And then we'll wrap up. Okay, so just as motivation, a very quick survey of all the things you can do with scattered interpolation. This is really an amazing tool, both in computer graphics and beyond. So just one slide each. So this is a 2008 paper in which Bernd Bickel and collaborators were learning to model dynamic wrinkles on a face. Facial retargeting is a very well-known problem now. One of the very first works on this was 2001 expression cloning, and it used scattered interpolation to transfer facial expressions from one model to another. Ken is going to go over a SIGGRAPH paper on using scattered interpolation to do non-photorealistic editing of NPR shading and highlight. It's been used to do artistic editing of fire, where you can recolor part of the fire and have the results automatically propagate to the remaining flames. It was used for the very first morphing, famous idea back in 1992 or so. It's been used for in-painting, so-called. So this is the problem where you have either a photograph that's been damaged and you want to fill in part of the photograph, or alternately in movie effects, often you need to fill in something that's not supposed to be there, and that may be something like a tracking marker or what have you. It's been used for lighting correction. So I worked on the Matrix sequels, and there was a scene where Keanu Reeves was flying over the city, sort of like Superman, kind of a stupid scene, but in that the city was photogrammetrically reconstructed from part of Sydney, I believe it was, and so people walked down a street in Sydney taking photographs and walked back up the other side. By the time they got back, the lighting had changed, so I employed scattered interpolation to correct the lighting on this. It's usable for reconstructing implicit surfaces from noisy point cloud data, such as you would get from your Kinect or from a LiDAR scanner. So this was a really great paper in 2001, Carr, Bateson et al. They showed a scattered interpolation method that is quite fast. So they were able to take on these point clouds that had, for example, 1 million points. The problem of colorization can be thought of essentially as a scattered data interpolation problem, where you have some scattered known colors and you want to interpolate that to the rest of the image in kind of a data-guided way. As I mentioned at the start, skinning can be approached as an example-based scattered data interpolation problem. In fluids, now I don't know anything about fluids, but evidently there's this so-called mesh-free approach, which is closely related to scattered data interpolation. And then lastly, just learning in general, machine learning. So one of the main approaches to scattered data interpolation was actually popularized in machine learning. Radial basis functions got popular in the early 1990s as sort of a replacement for neural networks, replacement in that they're reasonably powerful and sort of much more predictable. Okay, so just the definition. What do we mean by scattered interpolation? So in graphics, all of the textbooks cover spline interpolation, which we're going to call not scatter. We're going to call that regular interpolation. So if you have a spline mesh, for each U isoparameter, you have the same number of control vertices, and for every V isoparameter, you have the same number of control vertices. In scattered interpolation, on the contrary, your data points just have no structure to them, and you want to then be able to visit an arbitrary point and ask what is the value of our interpolated function at that point. So I guess because this idea, I'm not sure why. It's been around for a few decades, but textbooks do not yet seem to mention this, at least in computer graphics. Before the year 2000, there were only a couple of papers, research papers that used it, but since 2000, it's become a very, very common idea in academic research. Okay, so that was our very quick tour of application. We'll come back and look at just a couple of these in more detail, starting at 3 o'clock. Now, the next 40 minutes, we're going to go through as many algorithms as we can fit in the available time. So before starting off, I just want to mention this one slide here, this one concept. So in interpolation, we want the function to be smooth, but also sometimes you want it not to overshoot. And these two ideas are in contradiction. You can't have both. So let's consider these 2 points here. If we were to have a smooth interpolation that continues beyond that, it's going to have to go above that last data point. On the contrary, if you don't go above the last data point, you have a curve that's not smooth. Okay, so our first method we want to consider is simple linear interpolation. So this is something that does not overshoot. That's an advantage for some applications, but on the other hand, it's not smooth. It has corners at all the data points. So the basic algorithm is to do the equivalent of triangulation, which the higher dimensional generalization of triangle is called a simplex. So a triangle is 3 points in 2D. A tetrahedron is 4 points in 3D. The next thing is a 5D simplex in 4D, a 6D simplex in 5D, so on. So given a point, you search through all your simplices, find the one that contains it, and then do barycentric interpolation within that simplex. So this works. The main difficulty is that the number of simplices explodes in high dimension. So it's proportional factorially to the dimension. So we won't get very far with this method in more than, say, 5 dimensions. Now, if you were to turn off the internet and sit down and come up, just think for 15 minutes about how to do scattered interpolation, what you would come up with first is what's called Shepard's interpolation. So this is a weighted sum of data points. So d sub k is a data point, and we're going to predict the location of d sub k at a location, predict the value of d at a location P. And it's going to be a weighted sum over all of the data points. So WK at the current location times the kth data point. Now W sub k indexed by P is some weight function that is high at the point it's located at, and it falls off away from those. Now, we also have to arrange that all the weights sum to 1, so we're going to divide by the sum of the weights. So typically, W sub k is something like this. It's an inverse power of the distance between our current location P and some location of a data point P sub k, and then that's raised to a minus power. Now we notice that this is a divide by 0 if we're actually at one of the locations P sub k. So your program needs to detect that. Just check if you're at or numerically at one of the data points, and if so, instead of doing this computation, you simply output the value of the data at that point, which you already know. Okay, so here we're going to compare what it looks like with differing values of this parameter P here. So here's P equals 1. That's not very good. P equals 2 is reasonable for some purposes. It has this characteristic that it's actually derivative 0 at the data points. So you get these kind of flat spots. But on the other hand, it does not overshoot. Here's a P equals 5. Okay. Our next method, kernel regression. This is another method that you might invent just sitting down without looking up any methods. It's almost the same thing as Shepard's interpolation, but what we're doing is we're taking this weight function, which was formerly inverse power of distance, and we're just generalizing that to some arbitrary kernel function. Now, in so doing, so going back to here, we notice that at a data point it's singular, so your weight function is actually going up to infinity. Numerically, that's a problem, but it's also what causes the interpolation to actually interpolate. So in generalizing this no longer interpolates, it approximates. So here's an example where this is appropriate if your data is coming from Connect or something like that, where you know for a fact that it does have noise and you don't want to interpolate it. And now you're free to choose this this regression kernel R to be, some Gaussian, and if you want to make it more smooth, you choose a broader Gaussian, and so on. Okay, there's this method, Foley and Nielsen. This is a nice one in that it allows you to take a bad interpolation method and use that as a bootstrap and get good interpolation out of it. So it works in a couple of steps. As originally presented, Shepard's interpolation was the bad interpolation. But what you do is you interpolate onto a regular grid, and then now you have values on a regular grid. So when I say interpolate onto a regular grid, interpolate onto a lattice, a set of regularly spaced points. Now do something like tensor product spline interpolation of these regular values. Now you have a complete function, a complete surface, whatever it is, and you can go back then and query this function at your original data points. It's not going to be right, but it will be close. But now what you do is you take the residual, the difference between what you've just interpolated and the original data values, and interpolate that with a second low-quality interpolation back onto the lattice and iterate this procedure. So a way of getting good interpolators out of bad. Next method, moving least squares. This is pretty popular in graphics. So there's several slides of math here. You can look up the course notes, but I'm just going to mention what it is, the idea. So the idea is that you're going to pick some local model of the data. So you can say, okay, locally the data is smooth, so I'm going to pick a line or a plane to fit to the data. Or you could say, well, it's not that smooth, so I could pick a second order polynomial, so a quadratic. Now, what you do is at each point you fit whatever your model is, your line or your quadratic, to the data, but you fit it with weighted least squares where the weights are falling off with distance. So at every point you have a different weighted least squares problem. That problem is hopefully small. You've adjusted your weights so that the weights fall to 0 before you encompass too many points. So maybe at each point you're solving a problem of least squares problem of size 10 or something like that. And this weighted least squares problem, this local fit kind of travels over the surface. Now, one thing to point out is that moving least squares is actually a generalization of Shepard, or vice versa. Shepard's is a special case of moving least squares. So throughout the talk, or this section of the talk, I'm going to be using this set of data points. This is moving least squares applied to this with our model being a line fit local linear regression. So it's still not very good around there. Here's a comparison then with what is this, Shepard's and local linear regression. And here's a local quadratic regression, which still isn't all that great. So we'll be getting into some better methods shortly. Next method, natural neighbor interpolation. The idea here is to do a Voronoi tessellation and imagine that the particular point that you want to query is about to be inserted in this tessellation. So we're going to query our interpolation at this point. So we imagine we're going to retessellate, and we'll end up with this new cell here. We compare, for each of our neighbors, we compare the shaded area that would be introduced by this cell overlapping its adjacent previous cells to the overall area of that cell, and then that becomes a weight on that particular neighbor. So for for this as our point that we want to interpolate, we have maybe this area versus this one is maybe 0.3 or something like that, whereas over here, that little shaded sliver versus this is maybe 5%. So the weight on this guy is 5%. The weight on this is 0.3, let's say. Okay, so coming up, we're going to cover Gaussian process regression and radial basis functions. These are both kind of more powerful techniques. They're also closely related to each other. Now, in this, we're using this R as our kernel, and alternately, sometimes we use phi. It's indexed by distance between 2 points. If it's bold, it's a matrix, and R sub xy is an element of that matrix. This is an old paper of mine in which I use Gaussian process regression to generalize fractals. So fractals have a 1 over f type power spectrum, but that cannot do things like waves. So you can use Gaussian process regression to generate arbitrary power spectrum and thereby model either waves or stuff that has some oscillation to it. Now, before doing the math, I'm going to just mention quickly the interesting history of Gaussian processes. They were actually invented simultaneously or independently by Wiener and Kolmogorov during the Second War, so famous mathematicians. Then rediscovered in geology in the 1960s, where it was called kriging. By the time I got into graphics, this was kind of standard but kind of old stuff. And neural networks was the new craze, and this stuff was kind of being forgotten. But then late 90s, two things happened. One was somebody did an odd proof that if you take a neural network of the standard sort of backpropagation type and increase the number of neurons to infinity, the result is actually a Gaussian process. And at the same time, there was a benchmark on some standard machine learning problems in which Gaussian processes perform, more or less as well as a number of other methods. So in the last 10, 15 years, this very old method has seen kind of a resurgence. So it's a very simple method, actually. This slide is a complete derivation of the estimation. We're leaving out the variance part, but this gives you all you need to interpolate. So this first line here, what we're going to say is that the estimated value at some location, we'll call it t, where the hat here means estimation, is going to be a weighted sum of the data values at surrounding points t sub k. So this is a lot like linear regression, but it's different in that in linear regression you have y is a weighted function of x, where here we have y is a weighted function of y. Y is a weighted function of y at other locations. Now, next step is to introduce the orthogonality principle. So this is a generalization of the following idea, that imagine a table and imagine a point in space above that table. Now, what is the closest point on the table to that point in space? Well, you drop a perpendicular to the table. So another way of saying that is that the error, the residual between your point and the closest point on the table is perpendicular to everything in the table. So the error is orthogonal to the subspace that is spanned by the data. Now this applies in geometry, but in fact it also applies in random processes where the only difference is that it applies in expectation. So this E here is the expected value. So if you were implementing this in a computer program, it would be the average. But so in expectation, then, reading off this, the true value, which by the way we don't know, but it will disappear in a second, the true value minus the estimated value times all the other data has to be 0. Okay, so that's that line. Now the next line we just expand this out. So we multiply that over here, that goes there. We have another expectation on this side, and so that's what you get there. Now the last step in this is that it is the case that the expectation of the data at 2 separated points is called the autocovariance. It's also called autocorrelation. Now some qualifications here. We're assuming here that we've removed the mean and we're going to add it on later just to simplify everything. We're assuming that this is called something called stationary, so the statistics don't change over space. But with those, with those qualifications, where is my mouse? I'm doing this multiple screen thing of trying to find the mouse. Okay, maybe it will come back later. With the expectation of a data point multiplied by some other data point at a different location is the value of the autocovariance function. So this then results in a linear system involving this autocovariance. And the autocovariance, that's something that you can either measure from the data, or if you're an artist, you can invent one. And so notice in here that the data, there's no requirement on where the data is spaced. I called it T sub k, but k, that implies k is an integer, but it doesn't need to be an integer. It can be anything. Okay, so here's the result of Gaussian process regression on that same data set. This is with some particular covariance function that I've chosen. And so this is the first time I think we've gotten a nice smooth interpolation out of this. On the other hand, you notice that it's beyond the data, it's extrapolating off somewhat weirdly. Okay, so the last method, and this is the one we'll spend the most time on, is radial basis functions. So radial basis functions are nice. They're really simple to implement. They're smooth. They work the same in any number of dimensions. The idea is that it's a weighted sum of kernel functions, and there's a kernel function placed at every data point. So once again, there's my mouse. So this R is our kernel function. Its argument is the distance between our current location, P, and the location of some training data, P sub k. And so we're going to have a weighted sum of these things, and that's going to result in our predicted data value at a location P. So in pictures, let's take this blue guy. This is, for example, a Gaussian. We're sticking one down at the location of this blue data point. And here's a red one. It's the same one. It's upside down. We're sticking it at the location of the red data point, and so on. And now we're going to solve for weights that cause each of these guys to add up to the dash curve that interpolates the data. So a really simple idea. We're going to need to solve for these weights. Before doing that, here are some common choices for this R function. So Gaussian is the first one we'd think of, and it's intuitive. There's some odder ones, though, like in 2D, the thin plate spline is R squared log R. And to me, this is very counterintuitive. This actually increases away from the data, but actually it is the smoothest interpolation you can get in the sense that it's minimizing the second derivative squared integrated over the function that you're trying to solve for. So first let's look at RBF with a Gaussian. So here's a Gaussian that, choosing an R function as a Gaussian, that's a bit too narrow. So because it's too narrow, you get this drop down between the data points. Now we make the thing broader, and we get something that's reasonable and also doesn't overshoot. If we make it broader still, it starts to overshoot badly. Okay, so we need to find these weights, W. So this is a simple matter. We form a matrix like this. So this should be called R, but unfortunately it's called phi. Apology for that. But here, phi of 1, 2 means our radial function applied to the distance between data point 1 and data point 2. And so phi 1, 3 is distance between data point 1 and data point 3 passed to the Gaussian or whatever it is, and so on. So this is a symmetric matrix. You form this. Its size is the number of data points. Over here, you put the desired values, D1, D2, D3, et cetera. And so you've got a symmetric linear system that you can solve straight off. You can do it faster if you use Cholesky, which is suitable for symmetric systems. But now, if you're doing this in 3D, for example, this D1 would be, for example, the X component of your vertex. You would also have one for the Y and one for the Z. You would have 3 sets of weights, but one thing to notice is that this matrix here is the same in all 3 cases. So if you want, you can invert that just once and then apply it to the different dimensions, which is what I just said. Okay. Okay, so some variants of this. There's normalized radial basis functions. These are very similar to the Shepherd idea or the kernel regression idea, where what we're doing is doing our regression but dividing by the sum of all the weights. And so this results in something that is a little bit less sensitive to the width of your Gaussian if you're employing that as your kernel function. So here's a comparison of same points, same Gaussian width, but using normalized RBF on the right, and it doesn't have the dip down. On the other hand, it's insensitive up to a point. If you overdo it, you start to get this sort of steppy kind of effect to things. Okay, a minute ago I said RBF was the last method we were going to cover. I was lying. I'm going to now also talk about Laplace and Poisson, or biharmonic interpolation. These are sort of a dual to RBF interpolation, and they can also be applied to scattered data. After going over our applications, starting at 3, coming back at 4, we will talk about why these two things are related to each other. So the idea here is that we're going to minimize some measure of roughness integrated over the surface that we're trying to solve for. So f is the function we're trying to solve for. In this case, we have first derivative. We're going to square it because otherwise it might be negative, and we're going to integrate over that, and we want to minimize that. So the multidimensional version of this, we're going to minimize the gradient squared integrated over the surface. Now, a bit of useful terminology. So a function means something, you give it a number, it gives you back a number. An operator is something where you give it a function and it gives you back an entire function. So the derivative is an operator. You give it a function and it gives you back the derivative of that function, which is an entire function itself. So there's a concept of the null space in linear algebra. The null space is the set of things that when you apply an operator to it gives the result 0. So the null space of the derivative operator is the constant function. So meaning if you take some function and take its derivative, now you take that function, add something to it, and take its derivative. The two derivatives are the same, even though you've added a constant. So this comes up in solving these things. This null space is something that if you say you're going to minimize the roughness, that's not enough to pin down what the function is, so you also have to add something in the null space to pin things down. And so that's going to come up in the theory section. So some solution approaches to this. You can discretize your differential operator, and then it becomes actually a matrix inverse. There's iterative techniques. There's multigrid, which works particularly well when your roughness is a derivative, which is usually the case. Now, in the course notes, you can refer to this. I've worked out what this amounts to in discrete terms. And so here's discrete, I'll call it scalar as opposed to vector matrix. We'll move to vector matrix in a second, but the one thing I'd like to point out here is this is deriving the Laplace equation in physics, but in discrete terms. So we're going to say that the gradient will take the one-dimensional case, that's the derivative squared, and we're going to approximate that with our first finite difference. So just the difference between ourselves and the guy next to us squared. And let's say that the spacing is 1, so we don't have a 1 over h sort of thing. So take the derivative of this sum with respect to the point that we're trying to change. So that's u sub k, unknown at location k. Do this stuff, and it comes out with this pattern. So there's a -2. There's a 1 there, but because it's 1, I don't write it, and there's a 1 here. So we have a 1, -2, 1 pattern, which is the finite difference approximation to the second derivative. And to minimize things, we have to set that to 0. So that's saying the second derivative is 0, or in the multidimensional case, that's the Laplace equation. The Laplacian is equal to 0. Now, you can speed things up by doing all this at the sort of the matrix vector level. So now we're going to say that the derivative is capital D and it's in a matrix. So each row of this matrix is obtaining the discrete derivative at one point. So it's taking ourself minus the guy 1 over from us as an approximation to the first derivative. And then you apply that to your function. That gives you the derivative of your function. In null space terms, this has rank n minus 1. So there's the constant, again, is in the null space of this. So we can take a continuous objective such as this and rewrite it in linear algebra terms. And I'm doing this because, at least for myself, a graphics person, I'm more familiar with linear algebra, or more comfortable with linear algebra than I am with calculus by a long ways, and probably some of you are as well. This D times F matrix vector multiplication squared is the analog of this, and so we can minimize that with respect to our function f and expand out the square, and it's this. So it's F transpose D transpose DF. So we're going to minimize that with respect to f. You can do derivatives on matrix vector expressions, and the rules are actually quite similar to just regular scalar derivatives. And you come out with this, and so hold this in mind to the next slide. D transpose D is quite remarkable. It's this. So we started off, just to remind, we started off with this is our D. That's our first derivative. If you form D transpose D, you get back the the second order derivative. And so in math terms, this D transpose is the adjoint of D. Now, if you have a two-dimensional case rather than a one-dimensional case, you're going to get this pattern, which is kind of a famous, if you've done any image processing, you've seen this before. This is the Laplacian stencil in 2D. Now I have a nice program demonstration of using all this for painting out some spots on a dog, but depending on time, we'll do it as part of the applications. We'll come back to it. Now, here's something. The Laplace equation in one dimension actually is what we call linear interpolation. Now, to go up from that, instead of minimizing the first derivative squared integrated over the surface, we want to minimize the second derivative squared integrated over the surface. And that will give us a smoother function. It also has a larger null space to it that we have to fill in. Here's a comparison between the Laplacian interpolation and thin plate interpolation, which is the second, minimizing the second derivative squared. So the function that's being interpolated has positive values, positive spikes along the L shape, and it has negative spikes immediately adjacent to it and no other data. And so in the Laplace interpolation, you get sort of this spiky thing. In thin plate interpolation, you get a smooth result. Thin plate interpolation, restricting us back to one dimension, is the same thing as natural cubic spline. So here's our natural cubic spline applied to our data. Okay, so I think we've managed to cover all the algorithms. Just wrapping up this section. 1 second. Yeah, okay. So here's a comparison between all the methods we've covered. So Shepard's with p equals 1, Shepard's with p equals 2, moving least squares with a linear fit, moving least squares with a quadratic, a Gaussian process, Laplace interpolation, RBF with a Gaussian that's too narrow, RBF with a suitable Gaussian, RBF with a Gaussian that's too broad, normalized RBF with the same Gaussian, and cubic interpolation. Now, the one last thing here. We've talked about interpolation. The kernel regression approximated rather than interpolated. You can also do that with these other methods, and typically the way of doing it is using regularization. So this is a useful numerical technique anytime you're doing linear algebra on the computer. So here I've turned up my regularization parameter so that the curve is smoother, but it's no longer passing exactly through the data. And so the idea here is simply this: you're minimizing your fit to the data, but you're also going to minimize, in addition, the sum square of your weights. So you want your weights to not be too big as well. But there's this little parameter lambda that's the knob as to how much you want to cause your weights to be small, and normally you'll pick this lambda as 0.00001, something like that. So what that's saying is make the weights small, but only if there's no evidence to the contrary. So if there's anything happening over here on this side that says what a weight should be, this 0.0001 will not affect things. On the other hand, if your data is nearly collinear, you can end up with large canceling weights, and instead of getting like a plus 10 on one basis vector and a minus 10 on the other, this will cause you to get a 0 and a 0. Okay, so there's our regularization again. Here's an example of why you need this sort of thing. So this is a multi-dimensional example where I've set values at 4 corners of a plane in 3D space. And then I just interpolated, and I got this wildly oscillating thing. But then as I turn up the regularization, I get something more reasonable. So again, there's these 4 points are constrained to the plane, and there's a 5th point in the center that's up from the plane a little bit. So we would expect something like this, not something that has these crazy dips. Okay, and I'm going to skip this now. So we're at 2:45. Please come back at 2:55 in exactly 10 minutes, and we'll do the application section. Oh, and no, hold on. Don't go. Sorry. Come back at 3, but first, let's spend up to 5 minutes seeing if there are any questions. So, any questions?
So I was wondering, the thin plate splines in 2D, there are like some subtle variations. You can have the thin plate spline energy or the Laplacian squared. They are not exactly equivalent. I was wondering if you have some intuition how different these are. It's only different in 2D, 2 and higher D than not in 1D.
Yes, that's kind of a topic for the theory section, so I'm going to defer that to the last hour, 4 p.m. All right. Yeah. Any other questions? Okay, good. So come back. We'll start at 3 promptly. Hi, welcome back to the course on scattered data interpolation. So the next 45 minutes or so is going to be some case studies of applications. First off, I'd like to give an interactive demo of removing the spots from a dog. So in this program, it's a bit hard to operate from here. We're using both the trackpad and looking over at the screen. I actually can't see the screen in front of me, but so we can outline a region of spots, and then when it becomes a closed polygon, there it disappears. And so if you were to go up close enough to the screen, if the projector is good enough, you'd actually see there's some fur detail in the recovered region. So what's happening here is a 2-step process where first the program is using Wiener interpolation, Wiener filter, which is related to Gaussian processes, to kind of shave off the fur. So a Wiener filter is an optimal linear way of separating additive noise. I'm calling the fur noise, and I'm calling the overall luminance white versus black spot the signal. So I'm using the Wiener filter to shave off the fur. I save that. Then I do Laplacian interpolation of the intermediate, of the interior of the spot. That pulls it up to whitish, and then I slap the fur back on. So everybody asks, okay, well, what happens if you do it to the eye or something like that? And what it's going to do is it's going to shave off fur scale detail in the eye and put that back on. So you're left with sort of a ghostly fur pattern, eye pattern in the fur there. Okay, so this is using, this was my introduction to numerical methods. The first time I tried solving this, I discretized the Laplacian in 2D, and I gave it to an AX equals B, a standard matrix inverse, and it took 4 minutes, and the machine was running out of memory. And so I recoded it using multi-grid, and it runs that fast. And this program is in Java, by the way. It's not even a C++ program. So a good numerical method will outrun a good computer language every time, I think. Okay, back to the slides, and I'm going to hand over to Dr. Ken Anjo.
So Next part of this show is to demonstrate our recent works, and also it means we'd like to show you some practical approaches of applying these deep, like RBF or some other interpolation technique to our graphics programs. So let me first show you one of our recent work, which is about facial blend shape animation. In using a facial blend shape model, facial expressions at keyframes are edited by slider operations and then interpolated automatically by computer. However, as the number of sliders increases so much, the slider operations would not be a good way to make good and beautiful facial animations. So we try to make an alternative way for this by introducing pin and drag operation that can be done directly on the 3D face model. So this video shows these methods outline. Oh, sorry. Here shows the user interface of this approach, direct manipulation blend shapes. This is actually made as a Maya plugin for our workplace. Then on the right, you could see some bars. This is the slider. Then the artist can manipulate, making some different face. They manipulate this bars many times. And also, this only shows some portion of the bunch of sliders, but here we maybe less than 10 sliders here. But we sometimes moving sliders deeper or upper side. And also, in our case, we are now providing the direct manipulation method, so we can put pin, and we can drag some pins to make another face geometry. Then we have a new face model. Then it is automatically interpreted as a slider bars action. So let's see once again. So now slider is moved. And or we can move this face. And the green button means the pinned portion. Then you could see when we change the face geometry by direct manipulation, then we can see the slider also changed by that operation. Yeah. So if we take the blend shape approach, then the first thing we should do is to prepare target shapes. And then these, of course, need making animation. Typically, these targets are kind of special poses at keyframes. But, of course, we need lots of more keyframes, then we need to edit them. And, okay, so in making some tools in computer for blend shapes, we first formulate them as a big vector. For example, in this case, the B0 means the neutral face, and it has so many vertices on the face geometry. Then they are making the large, big vectors, as denoted here as by B0. And we have for other faces, for other targets, we also have some vectors as a kind of representation in computer. And we can have, we now have assumed, we have one assumption that the topology itself is, of course, the single one structure. And they can move topologically equivalent way. And general face, after making such targets as many vectors, then general face is represented as a weighted sum of them. So, like this. Or in vector, in using the big matrices for each column in such target vectors, then we have this expression, or more precisely, so for each coordinate values, we can see on the right-hand side expression. And now, from now, we rather use the delta form. We call it the delta form. It's a kind of we want to measure the difference between the target phase and the original neutral phase. So at the bottom of this slide, you could see the formula. Then we have a little bit slightly different expression of phase model by using the different large B, the big matrix denoted by B is having each column has a difference bk minus b0. So k is ranges the number of target shapes. So this could be understood like this way. In abstract sense, we have take the neutral phase at the origin, and we have some different phases by changing the weights. So, and of course, there are many good things or bad things for our animator to use this technique for making good facial animation. But very good thing is that very easy to use, and also the target shapes are directly made by the artists. It gives them very easy, understand of the whole face space. And also manipulation using slider is very intuitively done and very fast. Of course, depending on the face geometry's precision or the number of vertices or the experience of the artist who want to use this technique. But anyway, one bad thing, this is very serious. The bad thing is that keyframe setting process becomes very laborious if we need tons of target shapes. So we want to solve this problem by introducing the direct manipulation method. So this technique simply means a method to convert the edited result of face vertices by pin and drag operation, which are given, and which will be transferred by this method to slider operations. So this would be kind of analogy to inverse kinematics for joint control in robotics. So this is our base idea. And now let me briefly explain the algorithm. So we want to make the face geometry to the weights. First, W0 means the current face weights. So that means before editing, we suppose that we have that expression for face. Then we make some pin and drag operation. Then we have a new geometry. And that, in that case, we have such result is described as shown in the number 2. So Fm sub m equal m plus F0. Fm is a new face. So next, we extract the points that are kind of small vector which consists of the coordinate values of the face vertices that are fixed or dragged by direct manipulation. This then want to minimize the result, the difference between the new face position and also suppose that we have given the after manipulation result as a F sub A vector, then we want to minimize FA and minimize the difference between FA bar and F sub M bar. To make this minimization, this is actually pretty under constraints. So because a pin and drag operation typically deal with only a few face vertices. So as JP already mentioned in his talk, we need to introduce the regularization parameter to solve the following least square problem that is shown here. So we have the sum, the first term in the minimization term. The first one describes the difference between the actual phase position difference and also the original one. And alpha means the regularization parameters. And just delta means that take the difference before and after editing result. Okay? This is pretty, standard least square program. It's very easy to solve. But of course, alpha should be decided after by trying to estimate some several potential candidates. So let's see this result. This is the first animation is just made only by using direct manipulation. So the final phase is a little bit strange because we don't say that direct manipulation is super or rather than using slide operation. We should use both modes. So to get a much better result. So this is the result by combination of direct manipulation and slide operations. So the face much more, look prettier, I think. So as I told you, and also we made several tests using by our method, and by analyzing the solution of our technique, direct movement of a single point means many subtle movements of sliders. And also a single slider movement means multiple direct manipulations. So these are kind of complementary to each other. So both are advantageous in different circumstances, we believe. Next, let's consider the case where we have some prior data, or typically a motion capture data. Then we want to extract some phase futuristic movement, I mean the correlation between two different points. If we can learn something about these from the prior data, then we hope that this kind of editing process could be speeded up, made it faster. So to make it, we also making a learning version of direct manipulation blend. We refer to LDM here. So we suppose that lots of motion capture data are given in advance. And we also need to, introduce the direct manipulation method to make a better face or new variation of facial expressions. So in that case, we learn something from the prior data. So let me explain that algorithm. So first, GI means the input data. So here, sub I means the frame. Then G is a vector. At that time, I. G sub I means the vector, phase vector at time I. Then we consider the covariance matrix of them. And here we denote E0 is the mean value of these phase data over time, I mean, in the case of motion capture data. Then we get some, through the eigenvalue analysis, we have some a bit smaller matrix from A that U is given by the consisting of the eigenvectors, whose each of them has positive eigenvalues. So we discard the eigenvectors having 0 eigenvalues. So let's put it here as U. Then we have, suppose that we have the phase vector as phase vector as expression as shown in this first line. And this time we solve the following least square problem. The difference is very subtle but very important. This case, we didn't use Euclidean norm for the second term for regularization. here we use this kind of a little different norm, and we could call it RKHS norm later. But I'll explain later about these things again. But anyway, in this case, we made this formulation based on the Bayesian estimation techniques. So we suppose that something stochastic or probabilistic nature is included in phase geometry during editing process. So, but C is not intuitive, of course. So we want to convert the information derived from C to the original weight to make it shown as a slider operation. So, but it's easily done because we have this formula. Then we can get W, the new value of W from C directly using this equation. And also, conversely, C also can be obtained from the value of W. So we can change the slider's value once we have the new C value from the experimental data and direct manipulation on the first model. So let's take a look at the difference between the original DMB, direct manipulation blend shapes, and also learned version. Let me show you the video. Oh, it's too fast. So first sequence shows the obtained motion capture data. Then, as you see, the facial expression is not so exaggerated, just normal face behavior. Just want to see the correlation between the face geometry of, at two different points. So we just want to such normal face expression, facial expressions to get more variation in actual animation. So let's see. You know, the both animation made the same operations are applied. But on the left is a regular normal direct manipulation without prior data. Then the slide operation results is local. So just, for example, we are looking at the two eyes, but on the left, we're just making some movement. Face geometry's change can be seen only at the right-hand side. But in the case of LDM, if we learn something, the behavior of eyes motion from the prior data, then we have just showing, we manipulate on the right, which one? Left eyes, but the result could be propagated to the other eye. So we can have such kind of blinking behavior directly by learning the motion capture data. So you could see that, yeah, like. And also, as I told you, we have the formula between the coefficient C and the weights. We can always have such a difference as, slider operations. Everything can be translated as slider operations. So in this video, we use the three methods: original slider operation and regular direct manipulation, and learned version. Each one we can use at any time. So let's take a look at the results, some based on the direct manipulation technique of learning version. We could see such quite difference from the original data. That shows the power of animator and also these techniques. I mean, not only direct manipulation, but also slider operation is so powerful. Okay. So I think this case, these least square approaches give us kind of approximation under constraints. But roughly speaking, interpolation in our case is the approximation with constraints. Constraints here means the result of direct manipulation branch shape. So the phase geometry change locally. It is, of course, realized as the whole phase geometry is changed through our method. So it could be understood as an interpolation rather than approximation. In practice, I mean. Okay, next one is a kind of, again, learning stuff. In this case, we deal with the doodles, hand-drawn face or some other things. And we want to get some similar copy from very small database of doodles. This was old work a bit. So the problem is that we first suppose that we are given n similar input drawings. We call them doodles, like this. Oh, it's a bit too small to see. Anyway. Then what we'd like to have is the more doodles that resemble the input n doodles, like this. Okay, let me show such kind of things. And also we may have some more examples. So we'd like to make such variation shown on the right from the small database shown on the left. So first, take a look at the result. We need some interface to make this tool usable for artists or some other.
The first step in creating a latent doodle space is to create a related set of line drawings. Here we will draw a set of images of the same character looking in different directions with different facial expressions.
So to make a similar shape, we have some examples based under the screen. With smaller, thinner lines are shown actually, and someone will follow that shape and make similar shape. Now register the new face, pushing the button at the bottom, and make another one.
Once we have a satisfactory set of drawings,
yeah,
we can create the latent space. Each dot on the left represents one of the input images in the latent space. One important key to creating a good latent space is to have correct correspondences between the different strokes in the images. Here we can see many of them have been determined correctly by our automatic algorithm as described in the paper. However, some are not correct and require user intervention, which is facilitated by the user interface shown here. This is better now, but we see there's still something not quite right about the nose. The stroke directions are reversed, which can be quickly corrected. Now with the stroke directions corrected, things are looking much better. Now we can use the latent doodle space to implement a sort of probabilistic stamping tool. A new random doodle is created for every click of the mouse. By clicking and dragging, the user can interactively choose a particular doodle from the latent doodle space. Scaling and rotation are also controllable.
So in the video, we show this technique, latent doodle space. So let me explain that how to construct that space. So first, we have, as shown in this video, we have several, typically 4 or 5 similar hand drawings, in the case face model. Then we want to make a good correspondence between 2 line drawings, because each face model consists of many connected cross lines, and each line has described as consisting of several line segments. And we need to make a good correspondence between these 2 line drawings. But as shown in this video, there is no perfect solution to make it, actually. So sometimes we need manual intervention to make a correct correspondence. So anyway, but first we want to make such space as best as possible. So we first make such space we call a latent doodle space, which consists of similar drawings, and we also have some possible new drawings. And to make it, which is similar to the case of direct manipulation blend shapes, we use Bayesian techniques, because this problem can be considered as statistical or probabilistic problems. And in this paper, we presented this work, Eurographics, several years ago. Then we showed 3 different methods. But here, we'll show just only one of them. So it's very easy to explain, and also very, very powerful, actually. So two main stages we need to construct this latent doodle space. First one is, of course, we need some kind of parameterization of the whole space to specify the new face. To make it, we use the PCA. Then to interpolate the 2 new face models, we use the radial basis function. So how to make it? So as I told you, each line drawing has a structure which has, we could say this, we call it first a stroke, simply means a connected component of them. And each component stroke has several linears consisting of several segments. And in this case, we have 2D expressions. So we have in this case, not the column vector, but this direction vector, as shown in the bottom. So each line drawing means each line. Then each one starting from the X and Y coordinates on the screen, on the plane. So we have such a structure, and also we construct the large matrix depending on every drawings, having all drawings. But the line is not so big, as I told you, 4 to 8 lines. But this column direction, so many segments, so we have many large size of data. Then we applying PCA to make from this to analyze the covariance matrix again. Then we take the first 2 largest eigenvalues. Then this is a good candidate to describe to give us the parameterization, because as you see in the video, we searching for the new face on the flat screen, which means 2D, and it has 2 directions. Each one came from these 2 largest eigenvalue eigenvectors direction. And then interpolate each of ST, the coordinate values, interpolated through the simplet spline. So which is like In this case, as I told you, the space dimension is 2, and we suppose that we'd like to make the smoothness by prescribed by the number m. I will be explaining later. Then we have this kind of radial basis function, which called thin plate spline. And the general form of interpolant is shown in the final line. So we have also added some linear term, as plus bt plus c. Okay, next go to the 3D case. Here is a similar problem, but this case we don't need to apply the Bayesian estimation approach, but this case another aspect of the application of radial basis function. So first, let me explain the cartoon shading. Probably most of you would not familiar with this, but anyway, let me explain briefly. So suppose that we have given a 3D face model, then we make some add light and face color or something. Then we have the such intensity distribution. This is simply obtained as the inner product of face normal and light direction. And it should be normalized between 0 to 1. And we introduce some threshold. Then we have this kind of face. So, but this in many cases, this also kind of causes many trouble in making good face light and shape. For example, on the left, you would see the result obtained by using the conventional 3D lighting, and of course we're using toon shader. So we introduced some specific threshold to make which is bright, which area is bright, and which area is dark. So, for example, in the case on the right, so you would see some strange highlight around here and around here. So this should be avoided for the make a good character. But this side on the right, you could see much smoother and relatively, clearer appearance of the object just by. Still, in this case, we still use the 3D lighting, but also we add our tools effect to make this possible. So compared to this side, near the chin, you couldn't see anything on the right because it's darker area. But sometimes we want to need art-directed effect, like this, around this area should be a bit more brighter. Of course, this is almost impossible just controlling 3D lighting. So in our case, we can make it just by giving some keyframes, such artistic lighting, and they are interpreted automatically to make the final result. So to make it, we use the radial basis function approximation. So the goal is to make toon shader artist-friendly overall, but more precisely, we want to make the tool for editing undesirable shaded area much more beautiful, much more attractive, and also we want to add artistic light and shade to get to the original 3D lighting. So the second purpose is a bit more 3D oriented, but the first one could be kind of painting effect or such artistic side. We want to combine these two a bit contradictory demands. For example, from the conventional result, we want to make on the left through new techniques. So let's see some examples. Also, this video explains how to use it. Oops.
this video, we present an interactive technique for locally editing and controlling stylized light and shade. Here we show an initial animation using a conventional cartoon shader. The animation consists of a single light source orbiting around the model. If the resulting interaction of light and shade with the model does not create the look desired, typically there are few options available to the creator. Our technique allows users to locally modify the interplay of light and shade in a way consistent with the original animation. First, we demonstrate the ability to add shaded areas, in this case extending an existing shade boundary. With our technique, the results of an edit at one keyframe blend in seamlessly with the pre-existing lighting. Our technique can also be used to selectively remove shaded areas. In this case, the user has accidentally removed too much shade. This mistake is easily corrected by repainting the desired area with the shade brush. These modifications also integrate smoothly with the existing animation. Here is the result after a few more modifications. In traditional cell animation, light and shade are often made to violate the laws of physics in order to create a more expressive result. Sometimes, as with here, unrealistic lighting is used simply to create a more aesthetic image. That's also the case with the shade under the lip here, which unfortunately broke into two parts with the original shading. Sometimes shadows are added to indicate three-dimensionality. Non-physical shadows under the eyes are often used in animation to make a character appear more forceful or severe.
Okay, let's go to the next one. This shows some example animations based on this technique.
The first thing we would like to do with this animation is to remove the large distracting highlight that appears on the character's forehead. For this, we can make use of the intensity brush, which adds directly to the local lighting thresholds. Moving to another keyframe, we see that the highlight has not disappeared completely here, so we use the intensity brush again. Now the unwanted highlight has been eliminated completely. Here we use the intensity brush with a smaller offset value to make a fine adjustment to the lighting around the character's eye using short layered strokes. Here is the original animation in its entirety. Note that this animation features both a moving model and moving lights. Yet our edits blend in seamlessly even in such a dynamic environment. Comparing the two side by side, we can see first that light has been added to emphasize the character's jawline. And second, we see the removal of the previously mentioned highlight. In this example, we demonstrate the application of our localized lighting control algorithm to a continuous tone lighting model. In this cut, the director wanted to make the robot appear more backlit than in the original lighting, to set a more mysterious mood and to strengthen the key lines forming the robot's silhouette. This example was created using 2 keyframes. At each keyframe, a few quick strokes were drawn using the boundary brush to extend the existing light area. Then the intensity brush was used to further expand and fill out the light area along the top of the shoulder.
Okay. So let me explain briefly how to make it. So the main idea is very simple. We just want to modify intensity according to the paint strokes because we introduced the paint strokes, which would be a very basic operation for artists. So let's take a look at this area to enlarge on the right. So suppose that this is the given initial situations where the intensity given as shown in the bottom image, and by introducing the threshold, we have the upper image. Then we suppose that we just paint something to add more darker area. Then if we can make some kind of new intensity distribution, then we want to have a new area that a dark area is exactly the same as the specified dark area by painting. So how to make this? And also, suppose that we have for each keyframe, we get some such good light and shade by introducing the painting operation. Then we want to make, next is to make animation. So this information is stored as a keyframe information, and they are linearly interpolated to make a whole animation. And so, okay, let me explain how to make a new intensity distribution based on the paint stroke. So first, suppose that this is an initial result, initial situation before painting. So we have some threshold. So one dimensional crossing, we have some intensity distribution as shown in the bottom graph. So this is the original intensity. Then suppose that we give some paintings like this. Then the new area, relatively red area, brown or red area, should be added as a new dark area. So this is a new boundary between the light and dark areas. So we want to make this, for example, like just take a look at that area surrounded by yellow line. The other side is quite exactly the same intensity distribution, we suppose. So we just want to focus on that area near the edited area. So in that area, we have the new value here. So you could see at the boundary on the yellow, we have some new values. So we want to get such kind of new intensity distribution because dark area's boundary is denoted by a red line. So at that point, we should give the intensity value should be the same as the threshold. So we want to make such purple line as a modified intensity based on the paint stroke operation. So this model, face model, actually made of the many vertices, and suppose that we are triangulated of this model. This model is triangulated, so we have such initial distribution of the intensity values at each point. And to make the purple line as shown in the previous slide, we use RBF approximation of the intensity distribution. The red and yellow bold lines are intensity constraint lines. So these are constraint values are given. And at first, the system set the RBF constraint points where the mesh edges and the constraint lines are inserted by us using a simple linear approximation. And in our formulation, the RBF are the function defined in 3D space. So we deal with, of course, this is a kind of surface model, but we use the 3D RBF model to interpret these values. So to make, and in our formulation, we use this style, this kind of RBF function here. Phi means just absolute value in 3D space, and also px is again a linear polynomial. And CI here, we means the constraint point in the space. I mean the newly added intensity value assigned at these points. And here the L is the number of all the constraint points. So we want to decide the weights value, but the number of weights is L plus 4, actually, because here is for W is just, of course, it's W, the number of weights, of course, is just equal to the L, but we added the linear polynomial. It has 4 unknown coefficients. So totally we have L plus 4 unknown values. So for the given constraint, given values at the constraints, so that means the number of the constraints is L. So we have L linear equation as shown bottom, as shown the equation in the bottom. But this is just L. We need 4 more equations. So we further consider the vanishing moment condition, which means for any linear polynomial, this W and CA should satisfy that equation. So, of course, do you want to know why we need this vanishing condition? But I will explain later. Anyway, we have taken the 4 bases of linear polynomial space, constant x. Here we say, instead of x, y, z, but we say x sub y, x sub 2, x sub 3. We put these things, we have 4 equations. So totally we have L plus 4 equations to solve. And this is described in this way, so we can get good linear equations. Then this is very easy to solve. And we have the new values of W weights and also the coefficients of linear polynomial. And this is another topic is about the pod space deformation, which was originated by JP, but this shows kind of a little bit more advanced style to deal with hand motion. It's a bit more different way of behavior compared to the muscle movement or shoulder or some such kind of thing. So let's take a look at the video. In this case, and also in the case of JP's original PSD, they use radial basis function in Gaussian style. But this case, they also further use the normalized RBF with Gaussian style. So this is also typically a pod space technique. We used several examples. This may be a little bit different topic from today's our topic, but anyway, we need some kind of such registration for bones. Then scanning. You will see the RBF's effect, and to make animation as shape interpolation. In this case, they use the Gaussian type RBF. So one big question, when we should use which type of RBF and in which dimensions, what's the relation between the Gaussian type RBF or, for example, the thin plate style expression. So we need to investigate more to know the reason why we have such variation, why we could use these variations. So let's go to the theory. So, okay, we have the break? Yes. So 5 minutes break, so just come back 5 minutes later. I mean, it's now 3:45, so could you come back to here? 4 o'clock. Thank you.
Hello, and welcome back to the course on scattered data interpolation. This last 45 minutes is on some theory topics, and we're going to do this in 2 parts. The first part, first 10 minutes, 15 minutes, is on discrete theory, and this is good for those of you who, like myself, are better at linear algebra than at calculus, but then we'll move to the continuous theory and talk about things like the representative theorem and the polynomial side conditions. So when I was first using radial basis functions, one thing that I was always wondering is this RBF kernel. So you can use a Gaussian function for it, but let's say you're doing thin plate spline interpolation in 2D. The kernel function is this thing r squared log r. So I always wondered where does that thing come from? So this next 5-6 slides are a discrete explanation, discrete meaning not continuous, of this. Now, but before getting to the discrete side, I'll just set it up as the way it is normally phrased. So, so we have a problem of fitting data, and we're going to have a squared error. Now, that alone doesn't, if the data is sparse or scattered, that doesn't pin down the function yet. So we're going to say, in addition, we want the function to be smooth. And we express that by minimizing a roughness squared integrated over the function. So the function is f. This p is an operator that expresses how rough things are, so that is typically the first derivative or the second derivative or even a mixture of those two, as shown here. So if you do variational calculus, you end up with something like this, where you get the operator squared is equal to this thing on the right-hand side. Now, jumping ahead briefly to the answer, we're going to explain it better, but here's kind of the classic explanation. The radial basis kernel is the Green's function of the squared differential operator. So what is it? What is a Green's function? So here we take this squared. So squared meaning p transpose p. We take this squared roughness operator, and let's call it L. We're going to apply that to the function, and that is equal to some right-hand side. So let's not worry what the right-hand side is right at the moment. So this is, for example, taking the second derivative of our function is equal to some right-hand side. Now, imagine for a moment that we could express the function as a convolution of some kernel function g with our right-hand side. So the star here is denoting convolution. Now let's take this expression for f, substitute it into the equation above, and so we have this line, and so we have the right-hand side on both sides. Sorry, so the right-hand side is now on the left-hand side, so to speak. But so what this means is this equation, which is saying that the g thing, whatever it is, has to be the inverse of L in a convolutional sense. So it's a convolutional inverse. Now, if you recall, those of you who know signal processing, there's the convolution theorem, which says that convolution in time or space is equal to multiplication in frequency. And so, therefore, an inverse is a reciprocal in the frequency domain. So we can work out what this g is by taking Fourier transforms and take the reciprocal and then inverse Fourier transform. And that's sort of the right way to do it. Now, back to explaining this to myself, however, let's make 2 simplifications, and then we can do the same thing with some linear algebra. So the two simplifications are, one is let's imagine temporarily that we have regularly spaced data. So and its second simplification is maybe it's one-dimensional. So we have a one-dimensional function that we're solving for. So that's f sub k is samples of this one-dimensional function. Y sub k are the available data. And those data are sparse. We don't have data at every point, otherwise we'd already know what the function is. So we're minimizing this data fidelity term, again, subject to wanting the function to be smooth, and we're expressing smooth as minimize the roughness. So that's what's happening here. Now, here's our discrete version of the same thing. So we're going to take this roughness operator times the function squared integrated over the surface. In discrete terms, that's this thing. And now we're going to say that we don't have data everywhere. We only have data at a couple places. So let's say that there are 3 known locations of data, and everywhere else it's unknown. We're going to express that with what I call a selection matrix. So this is a 3 by n matrix where the first row, it's all zeros except for there's 3 ones, and the first row has a 1 at the location of the first known data point. Second row has a 1 at the location of the second known data point, and so on. So this then is expressing this squared error, but it's expressing it only in the places where data exists, and it's sort of zeroing out or ignoring all the other places. Okay, so this is our discrete approximation to the problem we're trying to solve. Oh, and by the way, so S is, well, here it says it's diagonal. It's could be diagonal or it could be sort of a wide matrix depending on how you set things up. The P, again, this is now a discrete derivative encoded as a matrix. So this is a Toeplitz matrix. It's band, how do you say Toeplitz? It's diagonal constant, off-diagonal constant. So each row is shifted over from the one above, and each row then is taking a discrete derivative of the function at a particular place. Okay, so now all we do is take this expression. We want to minimize it, so we're going to take the derivative with respect to f. And now it happens that if we're setting it up as diagonal, s transpose s is equal to s itself. Take the derivative, we get this thing. Pull this over to the right-hand side and divide by lambda. We have P transpose PF is equal to this thing. Now we imagine multiplying by G, and we want a G that cancels out P transpose P. So G has to be the matrix inverse of P transpose P. So that then is the RBF kernel in linear algebra terms. So in other words, P transpose P, every row of it is expressing a derivative at a particular point. And so thereby the matrix in its entirety is doing a convolution of the derivative stencil with the signal. Take the matrix inverse, and this is a symmetric matrix, so either in the rows or columns of this, you're going to see shifted copies of the RBF function. Okay, so that's my discrete explanation. Now we're going to switch over to Ken to talk about some of the deeper continuous theory.
Okay. So in my talk, I'd like to explain briefly the kind of theory about how we can derive the RBF functions using function analysis approaches. So first, let's recall the kind of thin plate spline stuff, and also shown in examples. So first, you could remember for example, the first one. I mean, the first equation expresses the general interpolant based on RBF theory or functions. Then, in the case of latent Doodle space, we use the thin plate spline, so Gx is equal in that equation. And it's followed by a linear polynomial. But in the case of 2D, we have just C0 plus C1, C sub 1, C sub 1, X sub 1 plus C sub 2, X sub 2. And in the case of Shade Painter, you remember, I showed some toon rendering stuff, toon shader stuff. Then we use the G, instead of thin plate spline, we use that very simple function, and also it's followed by a linear polynomial as shown there. But in the case of pose space deformation of weighted PSD, then they use the Gaussian RBF. And in that case, we don't need to add the polynomial term. So why? And also, let me review once again about the case of Shadow Painter. Then we have this formulation for describing RBF interpolant, and point constraint is given there in the second line. In the third line, we add the vanishing moment condition. And totally we have, as I told you, the L plus 4 equation to get all coefficients, not only alpha I here. Formerly, I weighted W sub I, but here we denote it by alpha sub I, and also linear polynomial P. So, as I told you, we need this here. N is a number of consonant points. And we need to solve the N plus 4 linear equation to get the function. So why? So where do RBFs come from, and why we need vanishing moment condition? And what happened for the case of Gaussian RBF? They don't need to add a polynomial term. So we could explain with the ideas taken from functional analysis in mathematics. So let's review the thin plate. So in the case of thin plate spline, we first consider the bending energy. It's also called the thin plate energy here, and it's defined in the first equation. This is functional, means for any sum, not any, but any sum of functions for phi, we could define that expression as an energy derived from phi. So we want to first, so let's consider first, we want to, what function can minimize this value? So to consider it, we first define the class of these functions. In this case, because we have the Fi, the value of Fi should be finite, of course. So we need to add some conditions on phi, like as shown in the second equation. So it's called as phi should be, square integrable for second derivatives. It's a condition to guarantee the first energy term should be finite value. Then, as shown, the L2 is probably you're familiar with this notation. The L2 space is defined as a square integrable function, the totality of functions which are square integrable. So second derivative should belong to that space. Then we have the new space. We call it Bepo-Levy space of order 2 and 2 variables. So let's find a solution in that Bepo-Levy space. So to derive some necessary condition for the minimizer to satisfy. So let's follow the Cauchy. Cauchy is a famous French mathematician, you would know. So first, F is such minimizer. Then we consider some functional So, but in this case, here we show that GTT is just a real number, and F plus GT is the function that belongs to the Beppe-Levy space. So then, if F is such a minimizer, then and also the G should be banished around the boundary. But in our case, usually considering that omega should be the whole space of R2, but in general, we can consider some bounded area in R2 space. So in that case, we add the condition to G. It should be banished around the boundary. So the second condition is necessary, but this is kind of tool for proof. Then let's consider GT again. Then we take it's easily to see that it's just a quadratic function of T and expressed in the final equation, and GT equals just a quadratic form and having such coefficients. And if F is the minimizer, then the derivative at the origin should be 0. Of course, F takes the minimizer. Then let's see what happens. So I would say G dash 0 equals 0. Then we have such equation. Then we apply the integration by parts twice, here and here. So you remember the familiar formula of integration by parts. Because G vanishes at boundary, so the residual term should always be 0. So we have such expressions. Then finally we have the last equation. This shows the biharmonic operator to apply to F times G. And G is arbitrary. Then we should have the biharmonic solution. F is a biharmonic solution and takes that form, the last line equation. So, and by the way, as JP already told you about the thin plate spline, but especially when we consider the biharmonic solution for delta function, which we could call a green function, then phi is decided as shown the R square log R form. This keep in mind for a moment. Now let's go back to the regularization program, which is given in that form. We want to actually find minimizer F in Beppe-Levy space, but for a assigned condition in the minimizer term, the first term should the constraint condition, and also it's added and F large F the functional of thin plate energy is added, and also lambda is a regularization parameter. We want to solve this one in the space of Beppe-Levy. Okay, this is a Beppe-Levy space. Now, explain a bit more about the thin plate spline case, but I first generalize the problem in n-dimensional case. And also for simplicity, we just consider the case where omega is equal to the whole space of Rn. Then to prove this is very easy to see this kind of the generalization of thin plate spline. We now consider the first term J and M is a new functional defined in that first equation. Here, the d alpha f is a kind of general derivative. But of course, we usually live in a 3D space. So we don't want to have n should be 100 or 2,000 kind of things, but just consider n equal 2 or 3, of course. Anyway, we have such a general functional as an alternative of thin plate energy in the case of 2D, two-dimensional case. So the problem is stated in the second dot. So for a given data, then we want to find a solution to minimize the second equation. So then we need to find a space where we can get the solution through the functional analysis. So first, I would briefly say about the function space. It simply means a totality of functions that share common properties. For example, we have many examples. The first one, the polynomial space, which sub M, where M means kind of at most, any polynomial that belongs to this space should be a polynomial of at most m's order. So higher order is just m. Not depending on the number of variables. And Cm omega is also a kind of mth order smoothly differentiable function kind of things. Also sometimes we can take m is equal to infinity. Means infinity times differentiable function, very, very smooth one, like exponential function. And C0 infinity omega means the subset of the second function space. Then it means the totality of the for infinity many times differentiable and has compact support, which means that it vanishes outside some big ball. And LP omega is also defined in the fourth line. This is also probably very familiar or well-known function spaces. Now, go back to the problem, regularization problem for Beppe space. As I showed you, this is the function we are now considering. And in the case of M and N take 2, then we have the original thin plate energy. So we have this regularization program now, and we want to solve this in the Beppe space. Okay. Then let's review there are several notations. Let me briefly review the meaning of notations. First, n is the dimension of a space, the number of variables, and m means degree of smoothness of the solution regarding J and M, which includes up to the mth order derivatives. And lambda is just a regularization parameter which specifies the trade-off between minimization of the first term and the smoothness of the solution described by the second term. So lambda is very important for practical use. So, of course, we just omit this rigorous proof of the theorem, but let me show the result first. So if M and N satisfy that condition, then we have a good solution described in the first equation. Here, G takes such form depending on the condition of 2m minus n, and P is polynomial. So also in this case, we need to consider the vanishing moment condition as shown in the equation at the bottom of this slide. So let me explain a little bit more about the relation of two conditions and the role of the GX. So again, this is the almost same information, but okay, in this case, we reviewed the RBF function we showed today for application part. So in the case of thin plate spline, where we take m equal n equal 2, and P shows the linear polynomial. And also in the case of shade painter, where we put m equal 2 and n equal 3. N is the space dimension of space, so 3. Then again, P belong to a totality of linear polynomials. But these cases do not include a case where a Gaussian type RBF is used. So it's a different situation. So let me skip this one because it's a little bit not so familiar with the computer science people. So let me, for more details about the functional analysis, could you take a look at our course notes? So this part should be skipped. And this is very interesting formula about JMN, the functional JNM. It's actually, by repeating, it's actually described in that first equation. This is similarly obtained as I showed you the twice used of integration by parts. In the same way, we have that formula. And if we consider the case where the functional J takes zero, then which means exactly means the same thing that F belongs to the polynomial space, which is at most order m-1. Then, interesting is that the Beppe-Levi space is described as a direct sum HMN plus P sub m-1. But this one, here we have the space we call RKHS, reproducing kernel Hilbert space. So let me explain this. But before that, let me recall the RBF interpolation. And as I showed you here, here, this for the composition, then the first term, actually the RKHS space, then we have this belongs to this space. And this space is a so-called normed space, which means have this space for any any pair of these space elements have its value as inner product. And inner product is defined in the last line. So it's a little bit complicated, but it's quite general, I mean, quite natural generalization of the template spline case. And then we show this very powerful theorem called representative theorem. Oh, need more battery. So since the solution, as shown in the previous slide, is represented as a linear weighted sum of Gx minus C sub k, what we should do is to find the finite number of the weights, which is the coefficients of this type of functions. And also we know that the problem should originally be solved in the function space, Beppe-Levi space. It's infinitely dimensional space. But now, according to this theorem, we just want to consider the weights, the weights of the function G of x minus C sub k. So considering just a finite number of functions weights means we just consider the finite dimensional space. It's very easy to consider. It's very easy to get a solution because we don't have to deal with the infinitely many possibilities. Just we want to restrict ourselves to the case where we just consider want to consider the weights only, and also the coefficients of polynomials. And also very interesting that this representative theorem is kind of surprisingly helpful for us to solve because, as I told you, the problem first originally considered as an infinite dimensional problem, but now, according to this theorem, we have just consider only the weights of finite number of functions. So it's very surprisingly powerful. So in a situation or in an example I've shown you today, if we set k in the first equation here, like this, then we can easily check that k is a symmetric, positive semi-definite function. And actually, this gives an alternative definition of RHS. Actually, I didn't tell about the exact correct definition of the RHS space, RHS, but actually, it's a kind of convoluted space with this kernel. But it's simply described just as a simple space spanned by this type of functions, and also finite dimensional. And also, CK can be taken as a value, as a position of constraint points, actually. So it's very, very convenient to solve. And also, what's G? G is actually characterized this equation, as John already explained to you. And this is, we can find for a delta function of that's satisfying this equation. G is actually described as shown here. And this is obtained from the potential theory in mathematics. So this is a kind of classical result obtained in mathematics. And we have this one. So the reason why we consider this kind of RBF function lies in the theory of potential theory and also the functional analysis based on these Beppe-Levi space approaches. Also, let's consider the vanishing moment condition. This condition actually follows from the fact that Beppe-Levi space is decomposed. One is the RHS space, and plus, already plus with the polynomial space up to m-1 order. And again, please remember this equation. If we consider the inner product, this is actually as a result of multiple times integration by time by parts. We have this formula of this notation should be missing. This is our mistake. Okay, let's consider. And what does this notation mean? It means this RHS space and polynomial space always orthogonal to each other, which means any element of this space should be orthogonal to polynomial space in the sense if we take the inner value, it always should be 0. So let's consider this one. So substitute this one, and if we take any arbitrary polynomial gx here, and here we say qx, then this term, this inner product term should be 0. As I told you, these two spaces are orthogonal to each other. So 0 equal the inner product here, and because of the linearity of taking inner product, we have the second right this equation. Then also you will remember this is a green function. This is a solution of green function for a delta function. I mean, for a given delta function, we have the solution that satisfies this equation should be delta function. So here we have delta function. Then you'd also know this famous formula. And here, please note the role of the notation. I mean, for the describing the inner product, we have now here L2 familiar, a more familiar inner product described in L2 space. Then we have this one. Oh, sorry. Sorry. Then, according to the definition of delta function, the L2 inner term between delta and Q should be the value qx at xi, x sub I. So we have this equation. So the vanishing moment condition simply means the orthogonality of this RHS space, RHS and polynomial space. So this should be satisfied. This is a necessary condition. So how about in the case of Gaussian RBF? Then we don't apply that discussion we made in the previous slides because the function of J should be different. Now let's consider such kind of infinite terms operators. But here, n just simply means a number of variables, so don't care about too much. And we have this one, and especially when we take the coefficient A sub m should, if we should describe it as like here, where sigma should be actually the variance anyway, but sigma should be positive. Then we have the Green's function for the infinite 3 times differential operators as shown in the second line here is the solution for this operator, and when we want to get the Green function, it's described in the form of Gaussian type. Then we don't need to add the polynomial term because in this case the space RHS space spans a whole space. No, we don't need any more to add the polynomial term. So usually when you use the RBF, Gaussian type RBF, then probably you wouldn't use the polynomial term. So this is a result from considering this kind of situation. Also, as a final remark, I just want to say the relation between Bayesian estimation, which we use for describing learned direct manipulation or doodle space. And then we usually use the Bayesian estimation because, as I told you earlier, in these cases, we suppose that the data could be described randomly or having some randomness or probabilistic behavior. So in that case, we usually use the Bayesian estimation approaches as a first trial. But when we consider the RHS space, sometimes we don't take care about such probabilistic element. So recall the case of learned direct manipulation. So then we consider the training data, motion capture data, and we have the covariance matrix first. We denote it by A here. Then we consider the eigenvalue analysis. Then we have the eigenvalues and the eigenvectors. And for non-zero eigenvalues, we suppose that we have U sub 1 to U sub R such eigenvectors that have positive eigenvalues. And we define a new, a bit smaller matrix from the covariance matrix denoted in the second line. And we solved to get a learned direct manipulation result by solving the minimization problem in the third line. By the way, so here we saw the very simple RHS space. Actually, it's the space spanned by the A. I mean, just we are now actually consider this space. Sorry. Oh, sorry. This space, I mean this one. This is just a notation. Very hard to use this keynote operation. Okay, here shows some notation where we consider every vector in Rn, And AX, of course, is a multiplied result, A times X. This space, and where, as you would know, the covariance matrix is positive semi-definite symmetric matrix. Actually, this is one of RKHs, which is finite dimensional, of course, this case. And its norm is defined by, in the second line, shown in the, very sorry, in the second line. So inner product is defined as shown in the second line, where F is equal A times X, G equal A times Y. But we should investigate the well-definedness of this inner product, because on the right side, we have regular, usual inner product, but we use X and Y. But A is, generally, it's a singular, so we need to check when we have the different Y, but it's such as, of course, for example, I would say F equal AX1 equal AX2, and G is equal to AY1 equal AY2. Then if we change the X and Y, we had the same result, of course, which means the well-definedness of this inner product. Actually, it's easy to check by hand. So this means the good, the regular standard definition of norm introduced for this very finite dimensional RKHS. So the important thing in introducing this idea is that now we can consider the deterministic problem in RKHS. Probably you would remember that in the case of regularization problem for Beppe-Levi space, then we don't consider any probabilistic behavior or possibilities. So instead, we just solve one in a deterministic way. But original Bayesian estimates assumes that the model to be discussed would be probabilistic or statistically treated. So we can, in a sense, we can eliminate such ambiguity coming from probabilistic formulation and understanding. So this would be also useful, and some statistical researchers or statistics researchers or mathematicians would also want to now, it's one of the current very big theme of them is that they want to describe every problem which is originally came from statistical issue or a probabilistic issue, but they want to rewrite it with only the idea of RKHS, so which means much more clearer and deterministic way to understand what happens in many phenomena. So I hope this would be a good influence for our graphics community as well. Okay. And finally, let me check the norm of this space. So suppose that F is described in the first equation, then probably you would remember that U sub is eigenvector for UI is eigenvector whose eigenvalue is positive. So we have this. I hope this could work well. Here we have this one because just same thing that described the first equation, and we can have this one because of the linearity of this matrix operation. Now let's calculate the norm in space A. Then as I showed you, the definition is need this term and this term. So here would be can be described this one. So we consequently have this value, which means it's actually the same value we introduced in the Bayesian approach for LDM, learned direct manipulation. So this is very good combination of good result obtained from RKHS theory, I think. Okay, so that concludes my part.
Okay, so wrapping up, one thing I'd like to mention, Ken and I have a recent paper in which we use RKHS to interpret both radial basis functions and Gaussian processes, and we actually show that they are the same thing, differing only in what you assume to be known ahead of time and what you assume to be evaluated on the fly, so to speak. We have, so the course notes for this course appear in the ACM digital library. However, we also occasionally update them with bug fixes and whatnot. So if you're interested in this area, please write down this website if you can see it. I apologize, it's a bit small. I'd like to acknowledge these people as well as Ken for teaching me a lot of math. Any questions or discussion points? Yes, I'll put this up. Actually, I'll leave this up as we're talking.